Today, let's take a look at simplifying radicals. You'll definitely want your perfect roots table, possibly a calculator, and your coral-colored notes sheet. In your Coral Notes foldable, open up to the second flap, pause this video, and write down what you see here. Again, you will need your perfect roots table as we're going to refer to this a lot today. Let's start off with the first example that you wrote down. We want to find the square root of 40. Well, if I plug it into my calculator, I end up with a decimal. So instead, we're going to explore how to reduce or simplify without variables. The first thing to make note of is this is a square root, so we want to look at the squared column of our table. I always generalize breaking down radicals as good radicals and bad radicals, meaning they reduce or they don't reduce. If you take a look at the squared column, what is the largest number that divides into 40 evenly? In this case, 4 does 10 times. 4 times 10 is 40. 10 is bad because it doesn't reduce anymore under the squared column. Therefore, I've reduced down to 2 radical 10. You might remember reducing radicals similarly in geometry class when dealing with your special right triangles. Let's take a look at example 2. This time, I have the cubed root of 40. Same process, but you need to look at your cubed column. Looking at your cubed column, what is a value that divides into 40 evenly? In this case, 8 goes into 40 5 times. 8 is a perfect cubed because it reduces down to 2, and I'm left with cubed root of 5. Follow the same process. This time I have cubed root of 72. Let's break it down into a good and a bad. 72, look at your cubed column. What number divides into 72 evenly? 8 does. 8 goes into 72 9 times. 9 is not a perfect cubed. Cubed root of 8 is 2, and I'm left with cubed root of 9. For example 4, same process. We're looking at the fourth root. Therefore, look at your fourth column. If I generalize, what is a value that divides into 512 evenly from the fourth column? It might take a little bit of guess and check, but 256 divides into 512 twice. The fourth root of 256 is 4, and I'm left with the fourth root of 2. Now let's explore what to do if we have variables. My first suggestion is to separate each piece under its own radical sign. So the 625 has a radical, and the x to the fourth has a radical. Always check your table first. Is 625 a perfect fourth root? And in this case, it is. It is 5. Anytime you're taking your index and exponent and they are the same, that is similar as saying exponent over index. Well, anything divided by itself is 1. So a way we can generalize that is if your index and exponent are the same, they just go away because they would end up being an exponent of 1. So 5x is my answer on this one. Now it's very rare that they'll both reduce down. Let's take an example where that's not the case. First, separate each piece under its own radical. Make sure you carry that index over to each of them. In this case, I have 64. If I look under my perfect cubed, it is a perfect cubed. It takes me to 4. Let's change this radical to an exponent. The exponent becomes my numerator. The index becomes my denominator. This is the easiest way to solve this one because that goes down to y squared. Bring down that 4 and we end up with 4y squared. Another way to look at it is how many times do groups of 3 go into 6? Well, 2 groups of 3 go into 6. Let's explore that idea a little further. Let's take a look at some more complex examples. Let's start off by separating each piece under its own radical. That should always be your first step. Now let's look at each one as a separate example. The 5th root of 4. If I take a look at my table, 4 is much too small. So we're actually just going to keep carrying that down. There is no good and bad for the 5th root of 4. Let's take a look at a to the 10th. Let's do a good and a bad to the 5th root. Well, if I separate the 10 to 5 and 5, right, when we have like bases, we add the exponents when we're multiplying those like bases. Well, 5 and 5 goes away and we're left with a. 5 and 5 goes away and we're left with a. That actually wasn't a bad root, it was also a good root. A times a is a squared. Another way to look at it is how many groups of 5 go into 10? 2, evenly with none remaining. Let's take a look at the b value. Here's where the good and bad will really matter. We've got 5th root. The 6 can be broken down into a 5 and a 1. 5 and 5 cancel, that's why they're good, so I'm left with a b. 5th root with the 1 power doesn't change. That's bad because it's going to remain there. I'm going to bring that down one more step so we have all of our values on the same line. The last step is just to reorganize. You just want to make sure if it doesn't have a root, it's out front, and if it does have a root, it's under the same root. Let's try another one. Radical 40x to the 5th. Let's start off by separating each value. Remember, our index is technically 2. Let's start off with 40 and do a good and a bad. Take a look at the 40. Look at your squared column. What's a number that divides into 40 evenly? The largest number that divides into 40 evenly? And in this case, it's just 4. The square root of 4 is 2, and square root of 10 just stays that way. Let's take a look at our variable. I'm going to quickly approach it from a visual perspective again. This means I have 5 x's underneath. I have 2 groups of 2, which means I can take x squared out, and I'm left with 1 underneath. Let's take a look at another way to look at that. Let's do good and bad. If I have 5, I can break that down into 4 and 1. 2 goes into 4 twice, so I'm left with x squared. The single x doesn't reduce, so it's just going to stay there. Bring down my 2 radical 10 and reorganize. If it doesn't have a radical, bring it out front. If it does, put it under the radical. The tough part of reducing variables under radicals is there's a different way to approach it for each type of learner. So find a way that works best for you, whether it be a shortcut, whether it be drawing it out, whether it be good and bad. Some of you might even have learned them using factor trees. Let me know which way works for you and stick to that method. For our next class, we're going to continue working on simplifying radicals. We're going to be working with partners, but just be careful that you might think of it differently than your partner. Make sure you stick to the method that works best for you. Make sure that you have your notes and your table ready to go. See you next time.